Welcome everybody to my today's presentation on Scala and ZIO. I'm really happy that so many of you came to this talk, and I'm really happy that you guys all want to learn Scala, and I'll do and I'll do my very best to show you why so many people are now going into Scala, why so many people are actually trying to learn this technology. I'll show you how current way of building high performance and highly concurrent applications is outdated, and why we need to rethink the core principles of how this software is designed today. My talk today is designed in a way that if you wrote Java ever in your life, you should be familiar with it, and it should feel still, it should be beginner friendly in essence. Yeah, hope you'll enjoy it. I don't see any of you because of the lighting, but I will have a Q&A session in the end. So to get started, first, this talk today is going to be done completely with Scala 3. So this is the latest Scala 3 that's been released. There are two branches of Scala, Scala 2 something and Scala 3. Scala 3 is essentially a new language. A lot of the stuff that's behind the scenes has been either rewritten or completely upgraded. And people do use Scala 3 in production now for a while, so both of them are valid options. The tooling is migrating from one version to another. Some of the libraries are already compatible with Scala 3. Some that, for example, use a lot of macros or very compiler-specific technologies behind the scenes will obviously need to adapt to the new Scala 3 compiler as well. So let's start with some basic Scala first. So this is essentially a function, right? And hopefully you learn enough math in your school that you know that this function should return what? It should add a number 1 to whatever you pass to it. So if you pass an integer, it will just add 1 to it. And there is beauty in this code, and my whole talk will revolve around seeking this elegance, this beauty in code. And the theory is that functional code, modern functional code, if it's pleasing to the eye, if it's easy to grasp, if it's easy to read, then it's probably written well, and it's probably something that you can build upon, and it makes sense. And if we translated that function that you saw earlier to Scala code, it usually goes like this. So you define function, so def is the keyword that you need to use. And in this case, you just need to also tell it that it needs to, that it accepts integer and it will return int. There are multiple ways how you can define a function in Scala. So here, for example, you have function add and function multiply. That are defined a bit differently, but again, you have very different ways of dealing and defining functions in Scala. Because you have so much flexibility when you define these functions, you can then build very complex and very complicated abstractions on top of it, and that's why the Scala as language is so scalable, and that's why you have very nice languages such as, I don't know, Akka, etc. And a lot of this stuff that we're going to see today wouldn't be possible if Scala as a language wouldn't be so extensible and so easy to scale. Now, below you can also see two additional functions, add multiply and add multiply 2. Both of these functions are essentially composed out of other functions above. So as a result, add multiply, you can see internally it uses add and multiply. So essentially, as you can read it, it will combine two functions together and give you another function that you can call as a normal function. So this way of composing functions is extremely powerful, and you can really make amazing stuff. Now, I don't want to talk much about other compilers or other languages, but I still want to mention this thing called currying. and it's initially defined or invented by Haskell Curry. And what you see here is a way how you define a function that supports currying. So which means the function will spit out another function that you can use. So a really nice use case of currying is, for example, if you want to do this kind of logging abstractions, you get in the end 2 functions that you can use, but behind the scenes you have currying. Very powerful concept. Obviously, Scala is extremely popular, especially because of its collections and because it's really easy to build more complicated abstractions or functions on top of it. So here we have one function that just sums number and returns the sum, written very expressively. We have another function that's written a bit in a bit shorter version, and in the end you also have function that first reverses the list, filters it out, and then you call just the sum function on top of it. So you can see how very readable how really readable can a logic inside a certain function be. You don't have to use the first version, you can also use the versions below. And Scala also supports generics, so same as Java. So in this case, we defined a function called myMap that accepts 2 parameters, A and B. It accepts a collection of something, and then you can also apply some function to it. And you can see that the generics enable you that you can run this function on integers, or you can run it on collection of strings. Again, compiler behind the scenes will check all these cases for you, make sure that string is actually string, that it's written on the right place, and you don't mix numbers and strings, etc. So the Justine's talk before me actually told how much work is now being put into tooling and languages, that they do a lot of stuff in compilation time, because that's all the work that compiler will do for you, and you don't have to do these things in runtime. And Scala and its compiler will do a lot of these checks for you, and will make sure that a lot of stuff is type safe as such. Now, I cannot really introduce you to ZIO directly before first talking about how broken is current way of designing software, and that you are all part of it. So I'll show you one example that you should completely understand, even you're not a Scala engineer. If you're a Java engineer, you should know about it. So first, and the first top lines here, you can see usage of system.getEnv. This is a function that's inside JVM, inside Java, and what it does, it pulls environment variable, and you can then use it as you please. And the problem with this function is that this function, you can see out of this usage, you don't know that this function can actually return null, which means that if this environment variable is not set, then you get null. And if you get null, then you have a problem either here at the bottom. You need to write a lot of logic to check if the value is actually null, or you need to just watch your log traces, because at some point you're gonna get into this null pointer exception, and the system that you designed will crash. So you have 2 problems here already. And additional problem on top of it is that this get environment can also fail with other exception that you might, for example, catch for, and it might, for example, raise security exception, and your code is not really ready to handle that. When I'm saying that this stuff is wrong by design, this is Sirtoni Hor. Hopefully I didn't pronounce correctly. But this guy is really famous computer scientist. Google him. He made a lot of interesting things. And he's actually contributed to this phrase or this quote that the null pointer exception or the null pointer reference is $1 billion mistake and has caused billions and billions of dollars of lost revenue when people essentially forget to watch for this null at some point. So he's just making a statement that this is and could be actually easily preventable. Then there are other attempts, or other guys that are actually struggling with this stuff. This is a post from Facebook, Meta, whatever they call now. Their engineering team is now working on this library called NPA. Essentially, it's a tool that they designed themselves that you can use inside your Java projects, and the compiler and the library itself will prevent you from actually getting those NPM and null pointer exceptions in your code. You can see, like, and there you can read the blog about it, and they explain how very problematic these exceptions are and how much work needs to be done in order to prevent this, because this problem is propagated so long. Now, if you ever done at least a bit of Scala, you probably saw this option thing. So to make this problem, to solve this problem in Scala, we use this option. So if you wrap this system get environment with option, the option will make sure that if something is null, it will return back what's called none, or it will return a value, right? So in this case, you'll get back either a string, the actual value, or you'll get back a none. And then because option is a special case, you can use it with your code, and you can flat map on it, you can filter on it, you can combine it with other options, and you can write really nice programs with it. And what it does is, if some of this get environments would be none, at the end you would get none, and everything would be handled for you. And a lot of today's Scala is written like this, and it's perfectly well written. The problem comes that system.get environment might raise an exception, and this program will still crash. Now, if you wanna be smart a bit about it, in Scala 3 you can easily make your own implementation of this option. And here, for example, I'm using what's new in Scala 3, what's called union types. So generic union type here in this could be, for example, means that this could be is either something string or it's none. And again, very similar implementation to this option that you saw earlier. But again, this is something that you probably shouldn't do. You should use option. I just want to show you how this is used. Okay, so if I go back to my first slide, and if we combine this knowledge that we just kind of learned, and if we ask ourselves, what's actually the difference between the first function that just returns one, whatever is number plus one, and the other function here, what is the main difference, right? So the main difference is that the second function is so-called impure function, which means that it interacts with either other world, outside of your context. So in this case, it calls system environment, and it tries to read system environment variables, and those can change. And if those can change and this function calls them, then it will return something different that you actually expect. Impure functions can also mutate something, some state in some other place. They can perform IO operations. So for example, reading from disk, writing to disk, or I don't know, network calls, etc. Now, at this point, you should probably be asking yourself, well, okay, but most of my code doesn't look like that first plus one example. Most of my code actually needs to send out HTTP request, or my code actually needs to do something, right? So impure functions are needed, they're necessary, and we need to build nice mechanisms around them so that they're fully embraced and fully supported in these modern code bases. So let's go back to this example then. Here we have first function that you see on the screen is called read all lines, and this is it uses the latest Java APIs to actually read the content from the file, and it returns, I believe, buffer. And then we use this Scala and dot to list, which will essentially convert Java's collection to Scala's collection, and then to list will essentially return back a list, a type inside Scala. So you get back a list of strings. Essentially, it reads the whole content of a file to a list. And the problem with this function is that we still have the same problem that we had with the environment. It can still raise an exception. It can still do something that you don't expect, and it's probably hard to detect. Now, you can do this in Java world or in Scala world. You can wrap these calls with try and catch block. So imagine writing around all your code these try catch blocks. And if something happens, make sure that you return something that's very predictable. So in this case, if exception is raised, I might just return empty list or something, and that would work. But the problem with these approaches is that you lose a lot of context. For example, you might get an empty list, but you don't know what actually happened, and you cannot react to something if you don't know what happens. Now, a better example might be this third example here. In Scala, you can still define or annotate your functions with this add throws and then class that of exception. But the problem with this is that defining exceptions on functions is not mandatory in Scala, and that this annotation that you see in your screen is actually just in Scala, just so that if you expose your Scala code to Java, the Java compiler will know that this is actually an exception. Now, if you use these functions, you can see here, obviously, the file that if you pass the file that doesn't exist, you'll instantly get an exception, and your code is essentially not correct as well. And this brings me then to this ZIO framework. And I'll try to show you a couple of tricks how ZIO actually takes care of these problems. And it goes like this. So the code that we saw earlier, that reading of files and then converting it to lists, etc., is wrapped with this attempt. If you wrap your computation with this attempt, it becomes a ZIO, or it becomes what it's called an effect. So instead of actually returning something, we're gonna start returning definitions. And this code now, the fingerprint of this code is now ZIO, all throwable, and list. And if we actually call this function, the code wouldn't be executed. The code at this point is just definition. I know that this sounds very abstract, but I'll show later what it means. But I'll go first to this ZIO definition. So ZIO has 3 parameters, and its interface or a trait. 3 parameters, 3 generic parameters. First one is for environment. Second one, E, is for errors. And third one, A, is for successful values. Or in our case, we have a function that doesn't have any external dependencies. It can crash by raising a throwable, or it can successfully return a list, which means that in the definition of the function, we now understand everything that we need to understand about what kind of computation will happen, and we can also understand what are all possible edge cases. There's nothing that can happen within that reading of file that is not described. We have like total definition of what's happening there. And these pluses and minuses mean, you can think of them that minus means that this what is being consumed, and plus means that this is kind of a thing that will come out of these computations. There are special wording for this, but I don't want to go into that. So how does like a very simple ZIO code looks like? It looks very simple and very clear, like this. So on top of it, we have this function that we defined earlier. Then you have these programs. In functional programming, these programs are essentially a way to build a very connected expression that it's not being executed until you introduce what's written here in the last part of the code, this runtime. So you define your program, you define your computation, you define your effects, and then you have runtime that actually executes it for you. Okay, so I know this was like very abstract. So I prepared this example that will demonstrate where this power comes from and how you can actually compose this thing. What we're gonna see now is gonna be a HTTP client. So it's gonna call out a web service. That web service is counter of how many people are currently watching TV online. And we're gonna try to like render the number of viewers that are currently watching this. It's a public API, and everything that you saw will be, you can check it out for yourself later on. But again, we're gonna try to get number of viewers out of the API. Okay, so it looks like this. So that runtime that I showed earlier, it's baked into this trait. So for example, if you just want to run this example, this is what you need to define. There is nothing else that you need to do in order to use ZIO runtime. So you define this app, and then on the bottom, convention states that you have this run method, and at the run method, you also define what the dependencies are we actually passing. So in our case, we're gonna use HTTP client, and you can see that the app now also has in the definition HTTP client as first variable, and this app can also crash with trouble, and that will be known at the end of the world. And the only actual thing that you need to know is that this data will come out of this this client call. And if we run this thing, after it's all compiled, etc., you get this number of currently watching people online. Nothing really fancy. You get the idea. Okay, and then let's try to make it a bit better. So let's say that when we're dealing with networks, they're unreliable, and it can happen that the service might go down or might be unavailable, and then your system will also crash. If we go back to this idea of effects, we can then do these things that you see here. So tapping error, whenever the error will happen, whenever exception will be raised, we can capture it and we can do something with it. In this case, we're just going to look into it. Or in the end, you also see this retry. So if this effect will crash, let's do exponential backoff. So it will try to slowly add time between the calls, and eventually, if more than three times this thing fails, then another exception will be raised, and the whole thing will come to a stop. Which means that you have this power of rerunning effects and controlling when they're executed, how they're executed, and how do you schedule them. If this is not powerful enough, you can extend the schedulers to do whatever you want. And when you run this example with some broken, let's say, host, you can obviously get an exception, you get another exception, and you can then notice that time is being added to these calls, 3 calls, and boom, then you get like the whole stack trace that something went wrong as completely predicted and expected. Now, to make this thing more interesting, you can also repeat effects. So we're gonna call this HTTP endpoint forever, but because we don't want to really DDoS the service, we're gonna add spice delay between them. So every 200 milliseconds forever, we're gonna call this service, and if something happens, this exception will be caught. And if we run this thing, obviously you get something like this. Every 200 milliseconds, you get a request, and everything works exactly as expected and predictable. And what else you also notice is the beginning, when the app is booted, you see HTTP async client started. ZIO can handle dependencies for you. In this case, I use this async HTTP client, and you need to start it. And when computation is done, ZIO will also call the close on you, and you have this way of cleaning the resources, and ZIO will manage the stuff for you, which means that you don't have to watch for any crashes and then do manual cleanups or whatever. And now I know this is getting really hairy, and if you never use Scala, it might be a bit lost. Don't worry, it will come better. So what we do now is these functions need to interact between each other, and these functions can also, for example, pass shared memory. So in this case, you see this line that says current ref.make, and then you have something and none. This means that I'm instantiating a new like a variable that can be set from wherever I want, and it's an atomic and it's thread safe, and the ZIO itself will make sure that nothing happens when you call these things. Ref is a very simple like primitive for dealing with data. You also have hubs, you also have queues, you also have other types, and ZIO also has what's called transactional memory structure. So, for example, you can combine mutations of the data into more complex things, then you have to commit them, etc. But essentially, it makes sure that if you have some very complicated computations, that you don't crash the system by, for example, making something silly. And in this case, again, we're going to call this service, and when we get back number of viewers, we're going to store that number into this current status. But we're going to also do something a bit smart. We're going to also compute if this number is bigger than the previous number, and then the new number will be stored there as well. And if we run this example, you can see that it's I added a bit more delay because it was too abusive to the client, to the server. But again, it's getting number. It's time for me to breathe a bit. And at the end, right about now, you're gonna see these arrows. So for example, the number dropped and then the number increased, which means that we computed the difference between number of viewers. Okay, now we're gonna try to do something a bit crazy here as well. We're gonna try to just shuffle the code out a bit. So hopefully you'll see that. Yeah. So here you see the app, and the app definition has this current stats that we had before. Then we have this collector, which is essentially what we saw earlier, the logic that actually collects the stuff. And then we're gonna add another function to it, or another service called server, and that server will actually serve out the content via HTTP server. And you can also see that I use this .fork behind at the end. ZIO internally uses fibers. So it has two thread pools, one for blocking operations and one for asynchronous operations. So all the computations that you saw on your screen, they are done in a synchronous way, but they are defined very linearly, which means that ZIO is already in the space where we're gonna go with Java apps when Project Loom becomes a mainstream theme. So fibers are used in ZIO. So again, on top you see collector. It calls this thing, update states, if logs progress, blah blah blah. And then you have this HTTP app, which is essentially definition of the HTTP endpoint. And then you have the server that you boot it up and it runs. And if I run this example like this, you can see that on top it's collecting the data. On the bottom, you have a curl request on this endpoint, and it's making requests. And at some point, the number on the bottom will also change because the memory was also changed. Okay. Okay, now I need to introduce what's actually written on the box of ZIO. So yeah, it's built it's built from ground up to be this modern, high performance library and ecosystem of tools that you can build to really build modern Scala tools, projects. It's type safe, which means that you saw that how types are used in order to define dependencies, how they're used to define exceptions, they're used to define the definitions better. Concurrent, as I saw, you use fibers and all the primitives to make more complex computations. And it's asynchronous by design, which means that, again, all the computations are actually executed in these fibers. There are some optimizations, but in general, it's from ground up designed to be extremely optimized in every sense. Resource safe, meaning that you saw the HTTP client. When the app was booted, it booted the client. When the app was being shut down, it stopped the process and everything. So it will make sure that you don't screw up with your resource allocation. Testable. When you're dealing with like high concurrence problems and high concurrence programs, there's a way in order to test this code in non-high concurrence way, which means that, for example, if you have any delays or any pauses or whatever in testing, you can just turn that off, and that will make your test suite very fast and very easy to work with. Resilient, I showed you how this effects actually protect you from doing something silly. And functional, again, I tried to demonstrate how very powerful simple functions are. And if you don't have simple functions, you can wrap them with these wrappers or concepts, and they'll become much better in a sense. And I have the last slide. So if these things interest you, if you want to learn more, there is a site called ZIO.tech. It has beautiful and excellent documentation. There is also extremely friendly. There's also a very extremely friendly community behind it. They will really help you. They're available and really eager to just accept you. So if you want to learn about ZIO, there's a lot of content being generated. There's a lot of talks, a lot of resources out there, a lot of companies adopting it. So yeah, you should check it out. I should also say that you have now not just this library, but you also have the ecosystem of these libraries. So for example, there's a library called, I don't know, ZIO JSON or ZIO Kafka or ZIO HTTP or ZIO whatever. So very similar to what we heard earlier from Quarkus and Quarkiverse. There is a collection of these libraries that are written in ZIO way, and you can use them off the shelf, and they're really, really, really well done. And ZIO, same as Scala, is written in a way that you can use all the existing libraries from the JVM ecosystem. So if you have any Java library out there, you can really easily wrap it in these things, as you saw earlier, and it feels very natural. If you have any questions, find me on LinkedIn, Twitter, and if you're Slovenian speaking, make sure that you listen to my podcast, our podcast. That's it for me.
Thanks, Otto. Any questions from the public? There is a question.
There's a question.
Thank you, not throwing the cube. I don't have very good depth perception. So this, to me, looks a lot like cats with sugar on top. Is there anything fundamentally different from cats with sugar on top? Is there like something radical and new here?
Yeah, I made the mistake of actually asking the author of ZIO that question, and it didn't turn out to be such a brilliant idea. There is a difference. Well, conceptually, cats is a library for functional programming in Scala, and ZIO is more like a concurrency framework in that regards. You really would need to compare cat's effect and ZIO, because cat's effect has these effects and runtime and everything that ZIO has. So comparing ZIO and cats is actually comparing React and Angular kind of a thing. But yeah, there are different ways of how this stuff is implemented. ZIO, for example, has this ZIO thing that you saw: environment, error, and success channel. Very strict, very defined. Versus cats, where things are not designed this way. There are also different things how runtime is implemented, and I don't want to go into benchmarks, but apparently ZIO is much faster because how it's implemented, and probably because it's a bit new. But both of them are really powerful and useful. I just think that ZIO is a bit more fresher, and because it's so friendly, and because you don't have to know much about functional programming, you can still build really nice programs really rapidly, really fast, and that is where I think the big difference comes. I think it's for cats, you would need to learn about monads, applicatives, monoids, functors, etc. And today you didn't see any of that stuff. You saw essentially beautiful code, and all that abstractions are kind of like hidden. And I think that's why this is why it's becoming such a popular framework in this space. Hopefully that kind of answers your question.
Hey, I have a question from maybe a more practical standpoint. So I agree that the code looks beautiful, but probably not to somebody not really familiar with Scala. So can you gauge maybe the trade-off of the benefits you get from using ZIO against having to onboard people unfamiliar with Scala, and how that basically affects the speed at which you're able to deliver things?
Yeah. Well, I had the pleasure of convincing a team to adopt Scala, and I had the pleasure of telling them which framework we're gonna use, and I had to evaluate that specific question. So, are we gonna use Akka? Are we gonna use Cats? Are we gonna use ZIO? Like, what the hell are we gonna use, right? And currently, I think like this stuff, again, community documentation, all examples, use cases, everything like that, it's newer and it's more friendly to beginners. That's my opinion here. ZIO is much more friendly. Again, you don't have to know what monads are, applicatives, all that category theory that you need to know in order to like fully utilize other frameworks. So I think in that regard, it's much better. In some cases, like the ZIO thing that you saw, it's being now replicated in different languages as well. So there is a I don't want to say port, but a lot of concepts that you saw here today are now being ported, for example, in TypeScript, and you have like TS effect or something like that. So I think once you understand why are you doing this, how you wrap this thing, what are these channels, you can really build things quite fast, and that I think is very powerful. And it's obviously it's possible to abuse or use these things improperly, but still the how these things are composed, how the compiler will prevent you from doing stupid mistakes, will essentially make better. You can do less damage with your code like that. Again, like for example, in JavaScript, you have TypeScript, and you have some safety that TypeScript will give you, but you can still do silly things because it's a silly language. Here, I think you have extremely powerful compiler that will at least take care of some of, like a lot of these errors. You just cannot do it because the compiler won't compile if you're doing something silly, and that's where this type safety will come very useful. So yeah, make sure that they learn.
Yeah, so one question, how can you combine this, can you call this from other JVM languages? So for example, can you have a team that builds something very mission critical in Scala and then call them from Java or Kotlin or whatever, Groovy, I don't know?
Well, I love this answer. It depends, right? So
that's a good one. Nobody's thought of that one.
So, well, obviously you can use what we saw earlier, either gRPC or any other channels out of the box. That's not a problem. But if you're asking me if you can use ZIO from Java or Kotlin, I haven't done it.
Well, can you, I don't know, build a jar or
Oh,
something
yeah,
and just
yeah.
include it into something else?
Yeah, I mean, you saw that example, all the examples were actually running Java jar. So it compiles into...
I mean, is it ergonomic? So I can ask you like that. So
yeah.
For example, if I use it as a dependency, like I have a project in Java and I include it in my dependencies in Maven or Gradle, and is it ergonomic to use?
At the end of the day, all the stuff that you saw, it compiles to Java. Yeah, sure. And if you can use it, you can use it essentially from anywhere. I don't... Yeah, where is JVM? Yeah, you're correct, obviously. And to make, I also need to state this. So you saw this running on JVM, right? But ZIO also compiles to JavaScript. You can run the stuff that you saw earlier on JavaScript without a problem. You change the compiler to either Scala.js and compile it via that. You obviously won't get thread pools and you won't get the same concurrency because of JavaScript. You can use that. I also use ZIO on front end, so you can call ZIO on front end and you interact with DOM. It's done. You can also use very easily. You can compile ZIO on top of GraalVM. You get all the benefits of GraalVM. It has been done. It's used like that as well. Yeah. And
if I may, one more. So you have the three components that you put into a library or an app. So the first one is the environment. Mm-hmm. Can you define what the environment can do wrong, like exceptions that can happen? Like, for instance, you had an HTTP client. Can that HTTP client say, I don't know, I have no more threads, or there's no networking on this box?
Yeah.
Can you define that?
Yeah.
Like this danger for its consumers.
Yeah. So ZIO actually has. I didn't want to go too much because this would be a very long talk. So you, like, for example, when I was wrapping that get environment function, at that point, you can say what is an exception that you want to handle in your code, and that is called an exception or error. Or you can say that you don't want to handle it, and then it's a cause. And if it's a cause, then you don't handle it in code, and the runtime will get it. So, for example, I want to explicitly just make sure that if I get security exception, I want to write something, react to it, whatever. And other exceptions, crash the system. You can still do that. So there is a way to convert exceptions to causes and causes to exceptions. Some of them are actually something that you want to deal with them, or you don't want to deal with them, and then the runtime will get them, and you get the same experience. So you have very fine-grained control over that. Yeah, sure.
About exceptions, what about stack traces?
Correct. ZIO has this, what's called like implicit tracing. So whenever you do these events, etc., you have traces embedded and they're inlined, etc. So whenever something happens, the ZIO and this tracing will combine these things, because as you saw, we are now splitting away the definition of the computation and actual place where this thing runs. So when exception happens, the runtime will actually match this and will tell you exactly at the line where something happened. So the runtime will actually map the computation to where exactly the problem has happened. That's something, for example, that ZIO doesn't, that cats don't exactly do like that.
Okay, but the stack trace.
You get stack trace.
Only of that particular ZIO imperative code.
Yeah.
Effect.
No, you get like, this is like point in runtime, and from there on, like you see everything. It's as you would expect, everything you see. You also get like information about fibers, so which fiber was used. You can also, it's pretty amazing. Yeah, you get everything.
this is actually tracked at runtime. How the control is passed from one
these
effect
effects,
to the other.
when these effects are actually being executed, you have some additional context so that if something happens, you see stuff. Yeah.
Okay.
Hey.
How would you handle writing application that uses actors?
Yeah, sure. Go. Actors.
To use ZIO. Is there any easy way to map the concepts of ACA to ZIO? And can we think about
a
fiber to be one actor, something like this?
There are okay. We have a little context. And I'll try to explain. Now there's the Lightband, so the company behind Aka, right, is now decided that they're gonna change the whole license model for Aka, and ZIO guys now saw that there's a really interesting opportunity to like take into that space. So if you're looking into using actors, if you're accustomed of using actors, there are now libraries built on top of ZIO that will mimic the whole mailbox and communication between actors, etc. So there are projects that are gonna replace Aka altogether, and they're very successful. That's one place that is actively something happening. You can use Aka. You can actually use it as you saw with this HTTP client. You boot up the actor system, and then you pass messages to it. You can do that. I think there's also Aka, some kind of interop library or something that you can use. In essence, you can build mailboxes. You have queues. So, for example, you can create a queue and you can consume messages for it, which means that you can build your own actor model quite easily. So there are like 5 options, but yeah, if I would need to know more specifics.
Yeah. In case you're writing some, in case you're writing some Aka application,
yeah,
you can easily architect using, I need this kind of object. It consumes the list of events, etc.
Yeah.
But how you deal with architecture when you write ZIO application? Because here you can compose the actions.
Yeah.
But how would you really think about the architecture? So, will you write thinking about fibers?
Yeah.
Or just thinking about computation and then try to combine this using this?
I think perhaps very similar architecture that you saw in this application, where you had like this thing that was scraping, and then it was when it got the message, it put it on the queue, and then you can have another like consumer that then consumes from this queue, and this is how you then, for example, build this separation of things, and how you can make things more modular. That's one way. You also have like this thing called hub, which can be used to send messages across, or this referential memory or referential maps or whatever. So there are ways how you can engineer. I would say this, like, if it doesn't look nice, then you're probably doing something wrong, which means flat. Yeah. I know some debates need to be held over beer. Okay. You good? Okay. And then thank you for your time. Yeah, please enjoy some drinks, and thank you.